All right, let's dive into a question that sounds incredibly simple, but is actually a masterclass in engineering precision.
I mean, you see one of these things thundering past a crossing, and you have to wonder, right? What does all that steel and glass and machinery add up to? 100 tons? Maybe 1,000? Well, the truth is, there's no single answer.
You see, a train's weight isn't some fixed number you can just look up. It's constantly changing. And for the engineers who have to design these massive vehicles, that's a huge challenge. Getting it wrong? Well, that's just not an option.
So, here's our game plan for this explainer. First, we'll look at the engineering problem itself. Then, we'll see how a solution called a reference mass gets built. We're going to compare the European and American standards, see how these numbers get used in real-world tests, and finally, we'll wrap up with why this whole system of rules is so critical for keeping us all safe.
Okay, so what is the actual problem here? Well, think about it. A train might leave the station empty, but then at the next stop, hundreds of people get on board. It burns through fuel, which reduces its mass. The brake pads wear down just a tiny bit, changing the weight again. So if you're an engineer designing a suspension system or calculating how long it takes to stop, which weight do you use? The empty one, the full one, something in between? You need a precise, agreed-upon number. To solve this exact problem, engineers all over the world came up with the idea of standardized reference masses. It's basically a way of creating a common language to define a vehicle's weight at different, really critical stages. We're going to start by looking at the framework laid out in the European standard EN 15663 because it's super clear.
And this just brilliantly shows the logic. You don't just pull a number out of thin air. You build it layer by layer. It all starts with the absolute baseline, the vehicle itself. Then you add everything you need to actually make it run. And finally, you add the whole reason the train exists in the first place, its payload.
So step one is establishing what's called the dead mass. Think of this as the train car's birth weight. It's the mass of the vehicle fresh from the factory, totally empty. No crew, no fuel, no passengers, nothing. All the parts, like the wheels and brakes, are brand new, totally unworn. This is our fixed, undeniable starting point.
Next up, we take that dead mass and we add what the standard calls design consumables. So this is the crew, a full tank of fuel, sand for traction, water for the bathrooms. You get the idea. It's everything it needs for a day's work. At this point, the vehicle is officially in working order, ready to pull up to the platform.
Okay, now we add the passengers. Design mass under normal payload is meant to represent a typical busy day. This isn't a holiday weekend, it's not right after a big championship game, but it is your standard busy rush hour. All the seats are full, and there's a specific number of people standing. This is the weight engineers design for everyday performance.
And that brings us to the final and most critical stage, exceptional payload. This is the absolute limit. Just imagine the last train home after a huge New Year's Eve celebration, with every single square inch of floor space packed with people. It's a rare event for sure, but the vehicle structure, its suspension, and its brakes have to be able to handle this worst-case scenario safely, no question.
Okay, so that's the very systematic European approach. But how do things look across the pond? Well, while the goal is exactly the same, safety through precision, the terminology and some of the specifics in the American standards are a little bit different. So, let's compare them.
On screen, you can see two of these key documents. On the left, we've got the American ASME standard for the structural safety of light rail vehicles, and on the right, a European standard for braking systems. Now, both of these documents, they rely entirely on having accurate, repeatable reference masses to define their safety tests.
Now, this is what's really interesting. Look at the language here. The European design mass in working order becomes the American ready-to-run load. The extreme design mass under exceptional payload becomes the very descriptive car body volume capacity load. See what's happening? They're different words, but the logic is identical. They're both defining the same fundamental states, a train that's ready to go and a train that is filled to its absolute physical limit. So why does any of this even matter? Why are we obsessing over these definitions? Because they aren't just abstract concepts for engineers sitting at a desk. No, they are the direct, required inputs for the physical tests that prove a train is safe enough for you and me to ride on. Just take a look at this simplified table from that American ASME standard. When they're testing the strength of the car body against vertical forces, gravity, the rule specifies using the car body volume capacity load. That's that exceptional crush-loaded weight. But when they test the force on the end of the car, it specifies the ready-to-run weight. The specific mass definition is tied directly to the specific safety test.
And it's the exact same story in Europe. This table is for braking tests, and it defines different European load levels, or EL for short. The brakes have to be tested at ELE when the train is empty. Then they have to be tested again at ELS with all the seats filled. And they have to pass the final test at ELX with standing passengers added. You have to prove, beyond a shadow of a doubt, that the train can stop safely at every single critical weight.
So when you boil it all down, these dense, super technical documents are all about one thing: creating a common language. They make sure that an engineer in Germany and an engineer in Ohio are talking about the exact same thing when they say a train is full. And that common understanding, that's the absolute foundation of safety.
Ultimately, it's not really about which standard uses which term. It's about the shared goal, this universal drive to achieve safety through relentless precision. Because when you're dealing with public transport, there is just no room for error.
These standards are really a kind of invisible architecture that keeps us safe every single day. So the next time you step onto a train, maybe you'll think about the incredible amount of calculation and definition that went into that one simple act. And it kind of makes you wonder, doesn't it? What other hidden rulebooks are out there, quietly shaping and